Hello and welcome to Cognito Key. Today we're diving into a really cool piece of computer history. Have you ever looked at old computers and just wondered, how did they do so much with so little memory? Well, the answer lies in an ingenious design philosophy called CISC and the incredible power of a single command.
So glad you could join us. Let's get right into it. The secret wasn't just about clever programmers, it was about the hardware itself. It was a core design philosophy born from just pure necessity, one that decided to tackle the problem by embracing complexity.
To really get it, we need to kind of hop in a time machine. Let's go all the way back to the 1970s, a time when computer memory wasn't just small, it was an absolute luxury.
See, the main problem was really simple. Memory was outrageously expensive. Every single byte was precious. Programmers had this huge challenge of squeezing every last drop of performance from their code, and this whole memory situation was a massive roadblock. So the engineers had a choice to make. If you can't make your programs longer because you don't have the space, what do? Well, you have to make the instructions themselves smarter, more powerful. And this idea gave birth to the era of the complex instruction. This solution was called CISC, which stands for Complex Instruction Set Computer. The goal was actually pretty straightforward, but really powerful. Pack as much functionality as you possibly can into a single command. The idea was to let one instruction do the work of many. Think of it like this, okay? Instead of giving a chef a super long list of tiny steps, like get the flour, now get the eggs, mix them together, preheat the oven, the CISC approach is like giving one single powerful command: bake a cake. The processor itself already knows all the little steps it needs to take to get that big job done.
And here's what that actually looks like in code. For simple addition, a RISC, that's a reduced instruction set processor, it needs 4 different steps to load the numbers, add them, and then store the result. A CISC processor, though, it gets the same job done in just 2. This meant shorter programs, which of course meant less memory was needed. But there's always a but, right? All of that complexity had to go somewhere, and it went directly into the hardware itself.
So how in the world did the hardware pull this off? How did it know what bake a cake even meant? To understand that, we've got to peek inside the CISC architecture.
Let's use another analogy. Imagine a general giving an order. The complex instruction is the big order, like take that hill. That gets fetched by the processor. Then it goes to something called a microprogram control unit, which is kind of like the sergeant. The sergeant translates that one big order into a bunch of smaller, very specific steps, like you provide cover fire and you advance to that rock. Those little steps are the micro instructions that tell the hardware exactly what to do. And hey, this wasn't just some theory in a lab. CISC architecture was the engine behind some legendary machines. We're talking about the IBM mainframes that ran entire businesses, the VAX systems that powered universities, and yeah, even the Intel 8486, the processor that really brought powerful PCs into millions of our homes. Okay, so this approach sounds pretty powerful, but that power definitely came at a price. The CISC philosophy involved a really fundamental set of trade-offs, and some of them had pretty big consequences for performance. On the one hand, the advantages were crystal clear. You get shorter code and programming is simpler, which, back in the day of expensive memory, was an absolute lifesaver. But the disadvantages? Well, they were lurking right under the surface. A single complex instruction could actually take a long time, multiple clock cycles to finish, and this created bottlenecks. Worst of all, this complexity really messed with a super important optimization technique called pipelining. You see, pipelining is basically a processor's assembly line. Ideally, you want a nice steady stream of simple, identical tasks moving through it. But CISC instructions are anything but uniform. Some are short, others are really long. It's kind of like having an assembly line where one station is building a tiny toy car, but the very next one is building a real car. The whole line has to grind to a halt, just waiting for that one complicated job to get done. So all of this brings us to the big question, right? What is CISC's legacy? And does it even have a place in our world today? Look, there's no question that CISC was a brilliant, absolutely genius solution for its time. It solved a very real, very expensive problem. But technology moves on. Today, memory is incredibly cheap and we have tons of it. The entire problem that CISC was designed to solve, it's pretty much vanished. So let's just recap the big takeaways here. CISC packs a lot of low-level tasks into single, powerful commands to save memory, but that complexity costs time, often taking multiple clock cycles. And here's the really fascinating twist. Its legacy is still alive. Most of the processors you're using today aren't purely CISC or RISC. They're actually a hybrid, combining the power of CISC with the speed and efficiency of RISC. Pretty cool, right? And that leaves us with something to think about for the future. As we move into this age of AI and massive data processing, what new complex problems are we going to need our processors to solve in a single powerful step? What do you think the bake a cake command of tomorrow is going to look like?
Hey, if you found this explainer helpful and learned something new, it would be amazing if you could hit that like button and subscribe to Cognito Key. Thanks so much for joining us, and we'll see you in the next one.